Hey there, my name's William and I'm going to quickly talk you through my poster, which I'll be presenting at the 2023 Anatomical Society Summer Conference here in Bangor, and which is centred around the growing problem of air pollution and the threats that it poses to neurodevelopmental health. So our focus is understanding the impact early life exposure to particulate matter and other environmental stresses has on neurodevelopment, using the zebrafish as a model. What are our two main objectives? We expect to observe changes in neuroanatomy for zebrafish exposed to these stresses, and we want to quantify these changes. Secondly, we want to confirm if this exposure leads directly to increased oxidative stress in the zebrafish brain. And so this section summarises the step-by-step process this project followed, and we're going to talk about this in more detail. Importantly, we use lipopolysaccharide, or LPS, as our second stressor. Given its success at triggering an immune response, we use this to essentially mimic a bacterial infection in the zebrafish. And here I've displayed some atypical phenotypes that we might see during this zebrafish developmental period, and which we categorized using these terms of severity at 5 days post-fertilization. Looking at the bottom figure, it was clear that the number of zebrafish with each category makes up a tiny proportion of each treatment group. This indicates that the low doses of particulate matter and LPS we're using aren't having any visible physical impact on the zebrafish early development. But this doesn't mean that there might not be any neurological impact. And so using immunofluorescence techniques and anti-acetylated tubulin, which is an antibody that stains the axonal tracts, we were able to observe a macroscopic overview of the zebrafish neuroanatomy. Between 3 to 5 zebrafish were used in each of these experimental treatment groups, and we observed some potential differences, and these are indicated using the white arrows. Different zebrafish larvae exposed to the same treatment groups as these were then imaged such that the regions of reactive oxygen species were observed. Now, this technique does require some refinement, but we still observed clear regions of oxidative stress, typically around the eyes and across the midbrain. Again, these are indicated with the white arrows as before. And then another angle to this project was behavioural development. Between 3 to 5 days post-fertilization, zebrafish were selected randomly from each treatment group and their movement was tracked. Here I provided an image of what the routes may look like as these days progressed. And when we analysed their movement data, we focused both on distance and velocity. However, we found that there were no significant differences between these groups across the 3 days analysed. And this is likely due to how early in their development we were monitoring their behaviour. So to conclude, we detailed 3 main takeaways, which I've touched on as we've talked through this poster. But generally, there are some observed differences in zebrafish neuroanatomy when larvae were exposed to higher concentrations of particulate matter and LPS. And it does appear that there is an increased reactive oxygen species in similar treatment groups as well. But finally, we finish on the next steps for the project. So most interesting that we had great success using zebrafish larvae in the seahorse machine, which is primarily used for cellular analysis. Even with a reduced number of treatment groups, as you can see in this figure here, there are still differences in the oxygen consumption rates, which are worth exploring in the future. And this provides another angle that the project can take. And so just to finish, I wanted to thank these 3 organisations, the London Interdisciplinary Doctoral Programme and RVC for hosting the project, and then also for the BBSRC Research Council for funding it. Thank you.